So this is what I will talk to you about today. We'll talk a little bit about the problem that we're trying to solve, why it is important and worth of our time, what kind of data analysis and visualization we're interested in. I will give you a demo of Google Earth. I hope it will just go flawless. There may be little glitches here and there. It's still an experimental project. And then I will talk a little bit about some suggestions that I have for future version of Google Earth. I want to say up front, this research is being carried primarily in the Laboratory for Atmospheric and Hazard Modeling. This is the primary place where I work. This is part of the CSER, the Center for Earth Observing and Space Research, part of George Mason University. We're also collaborating with the UNEP, that's the United Nations Environmental Program. And finally, we also have collaboration with NASA, and I will show you some of the nice KML that are being done by our students who also work at NASA. So first of all, what are we trying to do? We want to monitor and study and also forecast different type of hazards. What we mean is some of the most obvious, such as earthquakes, volcanoes, hurricanes, floods, but also things like atmospheric releases, climate change, global warming, heat waves, and so on. Why do we want to do it? Well, we want to organize and distribute the data and the scientific findings and make them universally accessible and useful. And I know you're pretty familiar with those kind of wordings. I just paraphrased a little bit. And what I want to show here that what we are trying to do, George Mason and in the research community, it's very much related to what you're trying to do at Google, so there could be some very good overlapping and common projects together. Why is it important? Why is it worth of our time? First of all, you know that every time that there is an earthquake or hurricanes, many people could die. We can also have billions of dollars in damage in properties. But then also, we can have some economic effect. Well, just yesterday I was talking to Livio as there are some very fixed routes for the shipping of goods from Asia, let's say China, back into Europe. And some of the shipping routes, they're in very seismic regions. So it would be enough that an earthquake strikes this region, cuts the sea routes, and then you will have immediately economic, global-wide economic effects. We can also destroy natural landmarks. We need to protect also the environment, create problems for very large areas. This is particularly true in our time, things like nuclear power plants or high dams, nuclear storage facilities. They pose us at a risk that is unprecedented. Never in our human history we were so much at risk from natural hazards. And finally, this is a concept that started in the Cold War, but it's true nowadays as well, is the destabilization of the military power. Natural hazard may trigger some local and regional conflicts. Finally, this is very important for the sustainability of our civilization. We need to protect our water resources and food supplies, which are the primary source for our living. As you can imagine, we didn't start today to look at natural hazard and all those problems. People have worked for, we can claim, even thousands of years. We have some reports of ancient Greece and ancient Romans that were trying to study scientifically, so not through mythology, just scientifically, earthquakes and other events such as volcanic eruptions. So why are we at an advantage right now? And the answer is observation, satellite observation. Never we had such a bonanza of data about the Earth. And we need to use such information to study the complementary nature of different parameters. Once, when all those hazards were studied only from a ground-based point of view, we had very sporadic data, and these data were primarily not complete. It was only giving small little information about the global picture. Whereas right now, with space-based remote sensing, we can have high temporal resolution, so we can get data every hour or every day, and with very high spatial coverage, and you've seen it primarily with Google Earth, you can go to a street level, but also at the spectral level, so we can see not only the visible, but also in other spectral bands. This is our This is our approach. We start from remote sensing. Those are the observations that come from the satellite. We feed them into numerical modeling, and those are what you see, for example, for weather forecast. So those are models that take the observation and then they help us forecast what's going to happen in the future. Then we have some data mining and data analysis, and here we talk primarily about spatial statistics, machine learning, classification, clustering, and so on. Then we have our data visualization, for which we use also Google Earth, and the distribution. And this is not the end. As you can see, this is a loop. Why? Because once we are done with our visualization and the distribution of data, this is a motivation to go back and look at the planet for a different point of view. Very quickly, I would like to tell you a little bit about remote sensing. I will not go into all the details of the satellites, but I want to make a big distinction. Probably what you're most used with are those 1 meter or so, even less resolution data that you can get into Google Earth. That is only some of what you can get from a satellite. What is also very interesting, some form of lower resolution data that go from 30 meters to 1 kilometer, but with different spectral bands, not only in the visible. Such data allow us to study, for example, the Earth from a thermal point of view. We can extract thermal information. However, as you can see, it's very hard to get everything at high resolution. Every time you work with the remote sensing data, you have to balance. You can get high temporal resolution, but then probably it's not spatial, or high spatial resolution, but not temporal and spectral. The reason because there is only as much an antenna that you can fly in space and as much computing that you can have in space. You certainly cannot fly a Cray supercomputer in space to analyze your data. So we have a trade-off. And this is why we have several satellites. And right now we have literally hundreds of satellites, both research satellites, military satellites, and commercial satellites, which every day study the Earth, the different spectral bands, and they give us very useful information. Also, what we try to do is a quantitative study. So we don't just look at the picture. We're really trying to look at time series. For each point on the Earth, we try to look at the temporal coverage. So in order to say, well, how did sea surface temperature change in the Gulf of Mexico for the past 10 years? And then by looking at this data, we can make inference about climate change, global warming, and so on. We have our own antenna, and I'm actually in charge of it. It's an L-band antenna. We get 6 satellites every day. 5 are from NOAA, which is the National Oceanographic and Atmospheric Administration. And then we also get the Chinese Fengyan 1 series. You probably heard about the Fengyan 1C series about a month and a half ago. It was very famous because it was destroyed using a ballistic missile from China. We used to get the data. So I can actually, if you want, show you some of the data that we used to receive from that satellite. Our coverage is regional. We cannot see it. Please.
So did they destroy it because they figured they were getting the data?
I don't think so. Actually, the satellite was, the main instrument failed quite a while ago. What he was just sending telemetry information, something saying, hey, I'm here, I'm still alive. But that was about it. It was not sending any useful data. But we were still checking every now and then, because you never know. Sometimes instruments, just by miracle, start working again. What I want to say that we have, we don't have a global coverage using the antenna. We have somewhat of a regional coverage, and I will show it to you. We cover most of the United States, part of Canada, and part of Mexico, which make us in a very good position to study primarily hurricanes. We get very good coverage for it. The title of my talk stresses about near real time. So why is near real time important, and why is it difficult? When you get data from the satellite, it's not just ready to be loaded into Google Earth or in other programs. You actually get some binary data. Those are just bits of information that are packed together and transmitted using this L-band or X-band signals. It's very hard. First of all, we need to acquire the data. And in order to acquire the data, well, you know where you are on the surface of the Earth, and then you can compute where the satellite is in the orbit, and then you just take your antenna, you point it to the satellite, and then you start getting all the data until the orbit is over. So there is first some challenging in knowing where the satellite is, try to compute for the exact position, because first, the Earth is not a sphere. Second of all, you know that there is some orography, so it makes it even more complicated. Furthermore, the Earth is spinning. And finally, the satellite is not always at the same altitude, because its altitude is relative to gravity over the Earth. And such gravity may change over time and may have certain anomalies. So first challenge is compute where the satellite is and get the data. Second of all, we need to calibrate. We have different instruments, and those instruments tend to degrade over time. And the reason is the space is a very hostile environment. Electronics is subject to cosmic rays, and even though they're shielded, there's still a certain degradation that happens over time. We need to compensate for this. Finally, we have cloud contamination. If you're looking at the surface of the Earth in the visible, you may have clouds. So even though you get good data, you're able to calibrate, then you look at it and it's useless for you. So you need to wait for the next satellite pass. Then geo-rectification, that's what I was talking about before, that you need to map what the satellite saw on the surface, and you have to take into consideration things like the orography and the fact that the Earth was spinning and so on.
I'm sorry, I didn't quite hear you.
Yes.
What was that?
Oh, what you need to do, oh yes, you need to take the data received from the satellite and map on the Earth, on the surface of the Earth. You need to take into consideration things like mountain, valleys, and you also have to take into consideration the fact that the Earth was rotating while the satellite was viewing. So you have very complex transformation that you need to apply to your data. You also need probably to clear some data. You may have some missing data. I didn't put it out here. Well, after we have done this, now we have usable data. Now, what do we do with it? Probably we want to put it into a model. If our problem is weather forecasting, we want to take the data that we have received with the satellite, feed it into the model, and there is quite some work that you need to do for this, and you need a supercomputer. You cannot run it off your laptop or off your computer. Then you need to index the data. This is something I think you're very interested about. And probably there are some issues that you may want to consider. How do you index data that changes over time, that has a spatial component, and maybe has also a spectral component? The same data may come in the visible, what you see with the eye. You may have some thermal channels and other channels, like in the ultraviolet. So how do you index this data, or how do you make it accessible for others? Finally, how do you distribute it? Each satellite orbit is huge. I mean, we're talking about terabytes of data that we received every time we have an orbit of a satellite. We can have several terabytes a day. So how do we store it? How do we subset it? Because probably people, they don't want the whole orbit. They're just interested in a small segment. And finally, security. Security and integrity of the data. Even though most of this data, you can find it over the internet, this doesn't mean that the security is not important. In fact, some of this data is the official data used by, let's say, National Hurricane Center to run their own model. So if this data is compromised, then you will get wrong model from a different agency. And arguably, I think it makes it very hard, the fact that the same data that you distribute to everyone through the net is the same data that government agencies are using for their own applications. So as we see, it's very, very hard to do everything in real time. Now, what I want to show you is the visualization. This is, well, you can tell it's me, and it's my office. I think last time I visited Google, I was very envious of you having 2 monitors on each screen. So I actually, I went back, and those are 12 30-inch monitor from the Apple, high resolution. And we built the structure together with 4 research assistants. And we get very good resolution. We can get to see almost the whole world at full resolution daily. As you can see, we put Google Earth just to prove that it could work. And it was quite an interesting project, to have so many monitors. We have right now 3 computers that are controlling them. So we have a distributed system, distributed graphic system to get an image, subset it, and then display it across multiple monitors. And I'm using this for teaching. Actually, I think it comes in the next slide. Okay, so what do I use Google Earth for? First of all, it's a visualization tool. So what I do to visualize and to distribute the data that we get from our satellite antenna in real time. This is I meant to say for natural hazards. And this is something that we are doing in collaboration with UNEP. It's a project that started at the United Nations. And we also have some collaboration with Google. I think last December also, if you came with us, we met in Mountain View to start this project going. And the goal is to release in near real time information about all types of hazards. We're not talking about natural hazards, also environmental hazards. So things, of course, as earthquakes, volcanoes, but then also air quality and different weather information, severe weather, and so on. So that's the first project. I'm using for teaching 2 courses. I chose the numbers of those courses. I thought it was funny, but I'm not associated with Boeing in any way. The first one is remote sensing of natural hazard, which I'm teaching this semester. And second one is satellite data acquisition, in which we cover the whole process from how do we get the data from the satellite to how do we post all the images online. We use KML to distribute our own satellite data, and I will leave those links. We have about 24 images every day, so it's about 1 every hour, in which we get data from our satellite, and within 5 minutes that the satellite receives the data, we post it online and you can see it. And it's quite, not too many people are posting satellite images within few minutes that they are acquired. We also use Google Earth for quick prototyping. Sometimes we get some data, primarily surface temperature we use a lot, let's say 2004 and 2005, and we quickly want to see if there is some changes, some notable changes between the two.
Are you using Google Earth Pro or just the...
No, just the basic one. Just the basic one.
Is that just because you wanted to avoid having to pay for the Pro, or I mean, did you look at it? I'm curious if there are features in the Pro that would make things easier?
No, for those things that we were trying to do, I didn't see any features that were in Pro. I will discuss some features that I would like to see, either hopefully in the free version, but also in the Pro version would be very nice. Okay, so let me give you a little demo. We will see about those monitoring of various hazards. I will show you how you can display real-time or near real-time remote sensing data in Google Earth. And then we'll show things as sea surface temperature and Katrina if it works, because I had some problem with it before. So let's quit this. And where is it? Crashed. Wonderful. Okay. All the work we've done, it crashed. So I'm going to load them in online. It's going to take a little bit of time. Let me add them. Do you have any questions? I mean, meanwhile I do this, please, we can talk. It doesn't require much. Okay. And I'm going to show the reflectance. So what I'm trying to do right now, to give you an image of how the Earth looks like viewed from space, pretty much in real time.
So you said the pipeline is supposed to be about 5 minutes behind.
Mm-hmm. Can you actually tell? Is there a way that we can say, all right, this is exactly 4 minutes ago or 6 minutes ago?
Google Earth, no. If you get the raw data, you can, of course, because there is timestamp in here. Not yet, but we can certainly do it. Some very nice suggestions for the future. Let me just show you. I'm going to make this a little bit transparent. Okay. So let's zoom in. And I will go here and show February. Okay. So here we're looking at the Earth. You can spin it. What we have clouds. Those clouds are as old as 3 hours old. Usually they're updated about every 3 hours. We have day-night, nighttime, so you can tell which part of the world the sun is shining, which part is dark. You cannot really see, I will show later about some texture mapping. Actually, probably I will. You can see like this. We have texture mapping from city lights. So those little white dots that you see are the city lights. You can see some very nice features. For example, the Nile. It's just so prominent. And Europe, you can tell the major cities. You know, I mean, I'm from Italy. You can see very well Rome, Naples, and so on. So the first thing, we know which part it's sun or not, and then you see a lot of little icons. Those red ones are forest fires. So where currently there are forest fires. Now, when we say currently, actually we say for the last 24 hours. And I cannot really say at what time, but for the past 24 hours there were some fires. Those little circle that you will see here, they are earthquakes. So they're earthquakes for the past 6 hours. And the red and yellow here, you have volcanic eruption. Red, it's a current volcanic eruption, whereas the yellow, it's something that shows some activity. It's not a full eruption, but either it was a full eruption and is cooling down, or it will erupt.
The data that you have that shows forest fires,
Yes.
Is that done programmatically, or someone physically following this?
No, all this is satellite based. So the way it works, there is a satellite, actually 2 satellites, Aqua and Terra from NASA, who have an instrument called MODIS. What this instrument does, he has several channels, and he looks at several different channels, primarily the thermal channel. Now, if he sees that there is an area that is highly vegetated with a very high temperature, then he will assign a certain probability that there is a current fire. Then you can go on and do a more realistic analysis in which you actually look at the plume, so you can actually see the smoke. This one in particular is just done with temperature, so there is a threshold. If surface temperature is above this threshold, then it means that there is a fire. I should mention that the data of the satellite, the resolution of the data is about 1 kilometer. Therefore, those are rather large fires. This means they affect 1 kilometer square. Then we have things like hurricanes. Right now, this is quite season for us, but in the southern hemisphere, it's very active. Those are hurricanes, once again, for the past few days. The ones that have a white ending, it means it's a forecasted. That's what the numerical model is telling us what the hurricane is going to be in the next 24 hours. The one that is just red is just the track, and as I said, those occurred within the last few days. I don't remember exactly how many, but it's a threshold that we can change. So this is just to give you a little bit of information about, well, that's how the Earth is and what we are looking at. Now, let me show you something. This is the climatological data viewed from space from February. Something that I never really liked about Google Earth was the way it does the texture mapping. This is how, here, the Earth really is. And this is what you probably are more, sorry, I need to remove December. So this is how, what you're probably more familiar with, that is the basic entrance to Google Earth. This is how I think it should be. So, and you can get, in order to show this data, this is a monthly composite. So what we did, we took all orbit for one entire month and then we put it together. The reason is that cloud contamination is that, you know, if you just look at one day, as we saw before, there is a lot of clouds. You don't really get to see how is the surface, how the surface looks like. But if you do a monthly composite, then it will work well. And in reality, it doesn't change much, you know, within a month.
If you had, say, the data for a month, and then a bunch of ground-based observations, would it be possible to sort of false image that?
Yeah, you can. It's a very hard problem.
Yeah.
You know, matching data, for satellite data with ground-based data is a very hard problem for different reasons. One, of course, is the resolution. Second one is probably the instruments are somewhat different. Even if the instrument is the same, when you have an instrument on a satellite, it has to go through the atmosphere, and the atmosphere will somehow change your readings. You have to compensate maybe for pollution or water vapor and so on. So let's say that it's very hard to combine satellite data, ground data. It can be done quite effectively for surface temperature. So you, for example, sea surface temperature, you can have a lot of buoy, and then you have satellite data, then you know you can spatially match it, and this is done. But for the visible, not really. What we can try to see now, I don't know if this works. I tried before, and it was a little faulty. It's sea surface temperature. This is a very important parameter which is investigated all the time when we talk about hazard, because it tells us a lot about the planet. It tells us about changes, whether the planet is heating up or cooling down. What we have here, we have monthly data once again for 2005. 2005, that is very important year because of all the hurricane activity that we witnessed in the Atlantic region. So, it's thinking. Okay, right here. So when we can go ahead and study the difference between month to month, or at least compare things like January with August, and you will see how there is a very strong seasonal component which can be studied very effectively. Such component, of course, affects global climate. It affects also the circulation and so on. One point I would like to make is, let's talk about hurricanes. Why do you think hurricanes occur? Do you have any ideas? Why?
Heat. Well, I guess it's, yeah, isn't it driven by what, picking up heat from the ocean?
That's true. But why? I mean, why? In nature, pretty much everything has a purpose. Yeah. Why does the Earth have hurricanes? And not only the Earth. We have observed hurricanes also on other planets. Well, the truth is that hurricane is just in a way, and actually a very efficient way, for the Earth to redistribute energy. It takes excessive energy in the equatorial regions, and then it moves them at higher latitudes. So what we see that if there is an excessive energy in the equator, then as a result we will see more hurricanes. And this is something that we can study very well with those satellites. So it's a little, it's thinking. But what this one is an image, I think what this is actually is December. And it's color-coded. Where you see red, it means warm water. Where you see the blue and the purple is very cold water. And you can see some features as the current of the Gulf, for example, or the Labrador current coming down. Let me see if I can zoom in it, because those are very... Probably there were too many in memory. Okay. So we can go ahead and compare, let's say, December, that it's rather cool, with August. You can see what a very large difference in temperature is occurring. Well, this large change in temperature is what is causing those hurricanes to occur. And by studying the spatial distribution of those anomalies, we were able to determine why Hurricane Katrina intensified so quickly. So let's say that the state of the art right now, we can predict fairly accurately what is the track of a hurricane. But we cannot forecast very well its intensity. So this is one of the unknown. And by studying the spatial distributions of those anomalies, then we may be able to give better approximations. And let me see if I can zoom in. This is for August 2005. where we had both Katrina and after shortly Rita. And you can see those patches of very hot water in the Gulf of Mexico. Those are in part responsible for the very rapid intensification. So as you can see, just by using Google Earth, we can actually study some very, very important phenomena. I'm going to wrap up and tell you a little bit about what I think should be done. Okay. Play. It's a little slow. Yeah, you got this spin. Yeah, you got the spinning pizza there.
Has used up all the memory.
Yeah. Well, it's nighttime. Right, there it is. Okay. Please. Okay, so first of all, some of the pros and the cons. First of all, the number of downloads, very large. It's very easy to use. It's a nice interface. Open API. It's free unless you get for the pro version. Then, you know, we all love Google, of course. Some of the cons, well, you can only do some qualitative analysis. Remember, before I was talking about how important it is to be able to study time series. That's something that we cannot currently do with Google Earth. We can only display the image and not the raw data. Something that would be very nice, now that I showed you the surface temperature, for example, just to concentrate in certain value. Let's say, let's display only what is between 28 degrees Celsius and above. It would be very nice to have another slide bar over there and just to concentrate on a certain range of data. Of course, you cannot do it if you're just feeding a JPEG because you don't have the kind of information, but you could do it if you're starting from the raw data and then build the color data according to certain legend that you define. Somewhat a limited API, there are things like time series analysis that would be nice to do that we cannot do right now. And of course, it was not intended for scientific, as a scientific tool primarily, but for the general audience. So what is my suggestion? First of all, allow Google Earth to read raw data. If you can read raw data, then you can start tackling a lot of problems that right now you can't, and it's a fairly easy thing to do. We can do some scientific experiments. So right now, Google Earth would be, instead of just a tool for the general mass to look at the Earth, to become something that we can use for doing science. We can get rid of a terrible problem about data formats. Remember before I said that we have literally hundreds satellites? Well, almost each satellite uses its own format. So by putting everything into one interface and distribute all the raw data into some common data format, we will get rid of this. That by itself would be a huge contribution. And what I think, personally, that Google Earth could become the de facto standard for GIS. I don't know if you heard about GIS. I really think that it could. All you need to do, as I was saying, to read raw data and to allow easy things like time series analysis. And one supporting evidence I have for this, that every time we go to conference, things like AGU, the American Geophysical Union Conference, which takes place in San Francisco every year, there are always more and more people that are using Google Earth to do some basic GIS. And if this will be extended to allow some time series analysis, as I said, or work with raw data, I really think that nobody would use different programs. It would be just the best. Another big advantage would be to provide near real-time information about the Earth. Why is this important? Well, once again, for our joint mission to organize the world information, make it easily accessible and useful for everyone. More broadly, how can Google Earth, how can Google help Earth science? As we saw Google Earth, but not only, you have very large computational powers. This is something that we're constantly struggling, especially in the university. Indexing, searching, and distribution of data with spatial, temporal, and spectral component. This is something that it's really at its infancy. There is some work done, but there is a lot of possibility, I think, for companies specializing in searches like yours. Something else, Google Base. It's a very good architecture to distribute data, probably could be tailored specifically for Earth science data. And finally, Google News, this is in the form of the hazards to alert different people about hazards. And this is the end of my talk. Thank you.
So what did you do before, I mean, so Google Earth is wonderful, and we've seen talks from people who are using it to do
Like things like watching birds in the jungle. That was a talk about years ago. But what did you do before you had Google Earth? I mean, you had all this data still.
Right.
But how did you visualize it?
It's really hard. We wrote our own software. By background, I'm a computer scientist, so I wrote a lot of visualizing software. There is some commercial software, all those GIS software, and this is what are primarily used in the scientific community. Very few people use Google Earth in the scientific community at this point. I think, one of the biggest contributions of Google Earth was really to make it easy for everyone to look at remote sensing data. I think it's one of the largest contributions. Right now, you have like little kids, like 8 years old, 9 years old, that they can go online and look at their home house, and this is something incredible. I mean, when we started, even just 4 or 5 years ago, and you wanted to look some data about the Earth, it was quite complicated, to get the data, to visualize the data, put layers on it, and so on.
So you said that right now it's only effective tool from a qualitative standpoint.
Right.
What would it, so you said it would be nice to have features that are more quantitative.
Right.
Also. What would that look like? I'm not familiar enough with Google Earth or what you're doing to really know what that would look like.
For example, I showed you different layers for monthly data, for the sea surface temperature. What you could do, just draw a little rectangle on it and say, well, show me the time series, and then the system would just show you the graph. And then from the graph you could see whether it is increasing, if it is decreasing. So do something that you can say, well, in the past 10 years the sea surface temperature increased by 1 degree. Like really put some numbers, not just visualizing, this area looks higher than the other. This is very important for science.
What's another example? So that would all the other examples be similar to that as far as?
Other example could be, for example, spatial distribution. You could compare two different parts of the Earth, in which I want to see what are the trends in the northern hemisphere with respect to the southern hemisphere. So you can do some also spatial comparison. But usually, every time we talk about quantitative analysis, we really mean to put some numbers to our findings. So time series analysis, the first that comes into my mind. Certainly this classification. What you could do, you could say, well, find me all areas on the planet where there is snow right now. The system will automatically create a mask. So analyze the different spectral, recognize what is a snow, and then put a mask on Google Earth. Or a pollutant release. This is very important for volcanic eruption. When you have volcanic eruption, it's very important for navigation. If you have an airplane and you fly through the plume, then you will crash. So, you could automatically say, okay, volcanic eruption, find me the plume, and then, it will map it in 3 dimensions, spatial and height. There are many. Those are the first that come to my mind.
I'm curious, do you also pull, with the research you do, you also pull population data also? So
Yeah.
I'm going to miss that.
Yeah, let me see if it works. That's actually something very interesting. Land parameters, population density. Let's see if it loads it. So what we do, we overlay the population density so that we can have some very quick estimate. Then let's say, okay, an earthquake occurred in this area. How many people are directly affected? It's right here. So let me remove the sea surface temperature. And this is population density for the whole world. You can see places like India and the Gangati Basin and China is much higher. So yes, that's something that we actually do and is a very, very important aspect of the research. Of course, we can only see just an image. What would be very nice to be able to click here and say, okay, how many people? How many millions? That's daily, probably it's going to be close to 20 million people.
Yeah, now if you look at something like this, you can really see where you could say, you just physically draw a circle around a given area and get an average or a total of folks there, or an average of some temperature or something like that.
Right.
So that's a variable.
And then if you have a time component, you can actually see the progress over time.
Right.
Thank you.
Thank you very much.